Um, okay, what we're trying to do is finish off 8.5. And there was one more problem in particular on 8.5 that I wanted to discuss. So let's go ahead and start with that. Does everybody have their sheet that says what they want to do for the test? I asked you to have that for me this morning if you hadn't turned it in. Can I have them? Let's go ahead and hand them in. Who handed them in last time? Oh, almost everyone. Okay. All right. 8, 5, 6. Okay, so we're picking up an 8.5 here. This is going to be example 8.5.6. So let's take a look at trying to figure out what sine of cosine inverse, it's back. The inverse trig function is back, plus sine inverse of 3/5. All right, now look, this is not an identity, all right? Something like this would be instructions here, find exact value. By the way, what we covered today is the last bit of material that will be on Wednesday's exam, all right? So anything we cover on on Monday will not be on our exam Wednesday, all right? So I'm going to try and get a study guide out to you. Hopefully, I know today's my kind of long day. I'm going to try and get a study guide out to you by tomorrow. What I'll do is I'll send that out via email, and I'll also post it on our website. And that way you can kind of get started and you can kind of narrow down your focus. All right, and I'm thinking of doing a handwritten one this time instead of just pointing you to problems in the book. Because sometimes, I might even pick problems from the book. If I write them down for some reason, it just goes better for students. So I'm going to do that. But give me till like the end of tomorrow, midday tomorrow to get that to you. All right. I'm also having a study group here on Friday. This Friday, my calculus class has requested that I be here for a study group. But if you as a group, a class wants to get together on Friday also, then I can kind of address both groups at the same time. But that's on you. You're going to have to get with each other. I think I said 9 to noon. I'll be available. So, I'm sorry? It won't be in this classroom. It'll be down in my office. But then if there's enough people, we'll move to a classroom. I'm pretty sure I'm going to wind up in a classroom because I think a lot of my Cal students are going to be there. So, okay? All right. So, wow, this problem is really odd because you've got find the exact value of this expression. We've never seen anything like this. We've seen like a sine together with a sine inverse, and that was it. But we've never seen like sine, and then inside of that, the argument being two inverse trig functions. They're not even the same inverse trig functions, and they're being added together, right? We have not seen this. But this section had to do with the sum and difference formulas, didn't it? Sum and difference formulas. So what I'm going to do is I'm going to try and get you to realize that this whole expression, cosine inverse of 1/2, I could call that U, and I could call this whole expression over here V. If I do that, do you agree that this problem is the same as sine U plus V? Do you agree? That's exactly the same then? Yes? Okay. If that's sine of U plus V, the sum difference formula tells me I can turn that into what? Sine U, right? Cosine V so get your formula sheets out, all right? Because you need to be able to turn to these and see where I'm talking about on your formula sheet so that you're ready for it when it comes to exam time. Is this right? Sine U cosine V? then what? Plus cosine U sine V. Does everybody see that? Yes? Okay. Then if I can replace my U here, right, with this and my V with this, but I just wanted you to see that this has the same format as the sine of U plus V, so I can convert it to that. Yes? Okay. Now what I'm going to do is I'm going to kind of stop for a second, and I'm going to look at U and V separately. All right? So let me look at what U is. U is equal to cosine inverse of 1/2. Now, we've done problems like that before. I mean, you've had homework problems where it says, find the arc cosine of 1/2. So how did we do this? We would draw a unit circle, right? Then what? Something very important I have to do, because it's an inverse trig function. Come on. Okay, thank you. Restrict the domain, right? Because it's inverse cosine, you have to restrict the domain. So I have to restrict it. So I know I cannot be down here because arc cosine is only defined in from 0 to pi, right? So I know that I'm in there, and I'm asking myself, when is this right here expression means when is cosine 1/2, right? When is the x coordinate 1/2? But you have to be in those quadrants. So where does that happen? Right up here at the angle pi over 3. And remember, inverse trig functions spit out angles, right? So my answer here should be an angle. Agreed? So this should be, U should be pi over 3. Are we good with that? All right, what's next? How about work on the other angle? Okay, the other angle was what? V must be sine inverse of 3/5. Now I'm going to draw a circle again. I'm going to restrict my domain. This time I restrict my domain to the first and fourth quadrant, right? And now I try and figure out where my what coordinate is what. Y coordinate is 3/5. It's not on my unit circle, right? But I'm in the first quadrant. Would you all agree? I'm in the first quadrant. So I'm even going to add in here, I can't be in here because I have to be in the first quadrant. Y'all okay with this? So we've run into a big problem because this one was easy. I just popped it right off the thing, right? I just pulled it right out of this. Right off the circle, I was good to go. Here I cannot do that. So I'm going to put a little question mark here, like how do we do this? And we could break out our calculator and do it. However, I want to just draw something for you. This point over here is somewhere, right? I'm just going to make it up, right? And if I wanted to, I could look at that point as being a right triangle, right? Something like that. And sine is what side over what side? Usually it's the opposite of our hypotenuse. So I could look at it kind of like this, couldn't I? That's kind of like this triangle represents the angle I'm talking about over here. Yes? Okay, now I still don't know what that angle is. So I still don't know what V is. I'm going to put V in here. Remember, that's our angle. I don't know what it is. But let's just proceed through the problem and see if we can address this, all right? This one we got, right? Pi over 3, we're happy. This one, don't know. So let's go back to what we wanted to find, which is this. Are we going to be able to find what sine of U is? Well, U we said was pi over 3, right? Okay, are we going to be able to find what cosine of V is? Well, we were trying to get V, right? And we couldn't get V right away. But we were able to draw a triangle for V. Now, if I come over here and I have this triangle, can you tell me what cosine of V is here? What is cosine by the definition? What over what? Adjacent over hypotenuse. You don't have the adjacent, do you? But you have two of the three sides of a right triangle, don't you? So can't you always recover this side? Do you see how important me drawing this triangle was? It's going to help me get cosine V here. So let's do a quick solving of this triangle. Sorry, that arrow angle was pointing at V, right? When I was pointing in here, that's our angle. I wasn't pointing to that side. The side here is what? You said it was 4, right? So you do Pythagorean identity, you know, a squared plus b squared is c squared, you get this side as 4. And that's great, because I now know what cosine of V is. Can I just put it in here now? Or do you want me to just wait to the next line? It's kind of up to you. Put it in? So what am I going to replace? Am I going to replace V with 4 over 5? What am I replacing? Cosine V, the entire expression, right? Because I want to know what cosine V is. Cosine of V is the adjacent over the hypotenuse. So all of that is going to become 4/5. Yes? So I'm just going to cross that out just so you know where it came from. This is 4/5. That's multiplication between those two. So it's sine of pi over 3, which I'll be able to get. 4/5 here. Then the rest of the formula is plus. Now, do you know what cosine of U is? Well, we should, right? Cosine of pi over 3, because I know exactly what U is. And do I know what sine of V is? Yes, again, off of my triangle, sine opposite over hypotenuse, this should be times 3/5. All right, and we're pretty much ready now. What is sine of pi over 3? That's the y coordinate at pi over 3, which is root 3 over 2 times 4/5 plus, what is cosine of pi over 3? 1/2 times 3/5. And now you do multiplication before you do addition. So multiply these two fractions together, which means multiply them straight across. Multiply these two, and you should get, let's see, 4 root 3 over 10 plus 3 over 10. You have the same denominator, so you can put those together. 4 root 3 plus 3 over 10. I'd say there's a lot going on in this problem, wouldn't you? I mean, this brings a lot of little concepts together, right? You got to understand, you have to understand one of the identities, and then you have to see that within the problem. Then you have to break it down. You have to try and recover what your angle is. If you can recover it, great. If you can't, you draw a triangle, and then you have to come back and plug everything in and put it all together. All right, so you'll probably see something like that on the test. All right, just be prepared for it. And I'll give you problems from your homework to practice. Okay, I think that'll do it for 8.5. I really hope that you did take some time to do the homework. I know some of you, I don't know if it's all of you, are actually doing your homework. For those of you who have really attempted the identities, I mean, you hopefully have realized that the only way you're going to get good at it is to keep trying and doing more problems. I mean, that's the key to the whole thing. All right, so some additional homework for you to look at off of page 650. I didn't give you these problems last time because we hadn't talked about that concept there. You can probably look at problems 73 through 77 odds. Those problems right there are just like the ones I just did. All right? Just like the ones I just did. Now, some of them involve tangent also and stuff, so let's just see how you do with that. It's same concept, though. Try to use one of the identities, break it all up, off to the races. All right, we have now the next section, 8.6. double and half angle formulas. These formulas should also be on your sheet. Can I see that sheet real quick? Double angle is up here on the right side, right below the unit circle. Half angle identities, I do not believe are on here. Let me see. No, okay, hold on. Yeah, the half angles are not on here. So what I will do is I will allow you to write the half angle identities on the back of this, or the half angle formulas, all right? So here you go. It's not very uncommon for formula sheets to be missing those because they actually come from another formula on there. So that's why they usually don't put them on there. All right, so what is the double angle formulas? Let's start with the doubles. I think I'll just put, well, I might put all of them. First one, sine, I'll write it the way it's written in your formula sheet. Sine 2u, right? Does it have it in parentheses? No. It does not have the 2u in parentheses, but please understand that the 2u is the argument there, so it actually is in parentheses. Sine 2u equals 2 sine u cosine u. This is a huge formula. Huge meaning it comes up all the time in Calculus 1. It comes up in Cal 2, Cal 3, and then you can always tell in a calculus class who's really comfortable with the trig stuff because we'll get to like, okay, and that's sine 2 theta, and then someone will be like, oh, but isn't that 2 sine theta cosine theta? And I'll be like, yes, good, you learned it. Okay, this is a big one to remember, all right? This is like the Pythagorean identity. I told you that one was an important one. This one is up there with that one. All right, so what does the formula say? It says that if you have twice an angle, there's a way to break this problem down to become just the angle by itself. So like if I had, for example, sine of, let me see, I'm trying to come up with an angle that would be a decent one to use. All right, let me try this. It's kind of trivial, but let's try it. Sine of 2 pi turns into 2 sine pi cosine pi. But I think this is too obvious because u is just pi, right? What if I had something like this, sine pi? Could you use this double angle formula for sine pi? Well, you would first have to be able to realize that you could rewrite that as 2 times pi over 2 inside, couldn't you? I mean, pi is the same as doubling pi over 2. And then the u for your problem now is this, right? U is this, u is this, u is this. So what I can do is I can rewrite this as what? 2 sine pi over 2 cosine pi over 2. I mean, very rarely would you ever need to break down sine of 2 pi because you know what sine of 2 pi is and you know what sine of pi is. But I'm just showing you how it doesn't matter what's in here. If you can rewrite it as 2 times something, then that's what your identity gives you. It gives you a way of turning that double angle into a single angle, if that makes sense. And now there's, for cosine, now there's only one formula for sine 2u. For cosine 2u, look on your formula sheet. Aren't there 3 formulas? Do y'all see that there? One of them is cosine squared u minus sine squared u. Another option is 1 minus 2 sine squared u. And another option is 2 cosine squared u minus 1. Which means that anytime you see cosine of a double angle, you have 3 different choices as to what, how you could break that down. And the one you choose is up to you, but is often dictated by what you're trying to do in the problem. I'll show you an example here in a minute where you'll see that we have to make some choices when we're trying to do this. All right, let's see how we can. Is there a tangent to U on your formula sheet? Yes. So tangent to U doesn't come up as often, but it's 2 tangent U over 1 minus tangent squared U. Or couldn't you say it's the same as sine 2U over cosine 2U? Wouldn't that be the same thing? I mean, tangent of something is sine of it over cosine of it, right? I think in all of my experience, whenever I've worked with trig functions, if I ever got something like tangent 2U, I always just figured out what sine 2U and cosine 2U were and just divided the two. I rarely use that formula. All right, so those are your 3 double angle formulas, all right? So let's just practice using these, see how we might see them in a problem. So 8.6.2. All right. If I tell you that cosine of an angle theta equals 3/5, and I tell you that pi is less than theta is less than 2 pi, find the following. Part A, sine 2 theta. Part B, cosine 2 theta. C, tangent 2 theta. All right, so there's 3 parts that we're looking for here. So let's start with part A. I need to know what sine 2 theta is, right? Well, I have a formula that I just gave you that says that to determine that, sine of 2 theta, what I could have is I could have turn this into 2 sine theta cosine theta. Now, what is it that I know about in the problem? I'm given information about what? Cosine of theta, right? Not 2 theta, right? I don't have 2 theta up here. I have theta. So I have cosine of an angle is 3/5. And I want to know what sine of double that angle is. So picture-wise, here's what's going on, if you want to draw a picture. And this picture may not match this problem, but just the idea here is this. I have an angle, right? Call it theta. Then if I double that angle, I'm going to be somewhere else, like maybe over here. That's twice theta. I know something about this angle here. I know in this problem cosine, so I know the x-coordinate, don't I? Yes? Basically, I know something about the x-coordinate. This I know. From that information, from just knowing theta and the x-coordinate at that point, I want to know all the information about what's happening at this angle, at this point, which is twice the angle. Yes? That's what's going on geometrically. All right. Now, so using the formula, what's nice about it is I need to know what sine theta is, and I need to know what cosine theta is. If I know what that is, I'm done, right? Do I know any of those? I know what cosine theta is, right? I have it. It's given, 3/5. So I'm happy about that. The only thing I don't know is what sine theta is. So how am I going to figure out what sine theta is? Draw a triangle. Now, keep in mind, we're given that cosine theta is 3/5, so that's like adjacent over hypotenuse, right? So I could draw a triangle right now. Now, depending on how comfortable you are here and how this has all gone into your brain, you can view it 2 ways. I can just draw a right triangle, and do my adjacent over hypotenuse. Or I could also take into account the quadrant I'm in. Because I have a quadrant restriction here. My theta has to be between pi and 2 pi. That's the way I prefer to draw it. Look, I'm gonna go here and I'm gonna be like, look, I cannot be up here because it says I have to be down. My theta has to be down here, right? But the fact that cosine is 3 over 5 means cosine is positive, right? What quadrant then must I be in? If I have to be in these either 3 or 4, but cosine has to be positive, then I have to be where? I have to be in the fourth. So I can eliminate this because over here cosine is positive in that fourth quadrant. So when I draw my triangle, I'm going to draw my triangle down in the fourth quadrant instead of trying to draw it just a regular triangle. So it's going to look like this. Here, here, like this. I know what my hypotenuse is, right? My hypotenuse is 5, and I know cosine theta 3 over 5 means my adjacent is 3, right? My adjacent is 3, which means that this side on the triangle should be 3, right? That's my x-coordinate is like 3. Now, why is there value in me drawing it this way? Why do you think I think it's important to draw it this way? What's my y-coordinate going to be here? -4, right? If you draw your triangle the other way, you may lose sight of the fact that because you're in the fourth quadrant, your sign must be a negative number. So I'm going to have -4 here. And again, I solved that just by doing Pythagorean, right? Understand? This almost, I would say, out of the last test I gave you, I think a lot of you missed that problem. And I took off 5 points. It was worth 10. I took off 5. You got all the numbers right, but the signs were off. Do you all remember that? Okay. So don't make that mistake again on this test. If you're given a trig function's value and you're given a restriction, you have to determine what quadrant you're in before you figure out what the signs are. Okay. So because of this, I take that triangle and I can now determine that sine of theta is what? Opposite over hypotenuse, -4 over 5. Yes? And now just plug this in. So sine 2 theta is equal to 2. Sine theta, we just said, was -4 over 5. And then times cosine of theta, which we were given in the problem to be 3 over 5. And just multiply everything across here. 2 times -4 is -8. Times 3 is -24. So -24 over what? 25. That is sine of 2 theta, -24/5. Now, just out of curiosity, if I say sine of 2 theta is -24/5, can you tell me where the angle 2 theta is? Can you tell me what quadrant it's in? Can you narrow it down? I'm saying that sine of something, right, is negative, which means I have to be where? Either 3 or 4. So look, the original angle theta, we know that it was in the fourth quadrant. But if you double that angle, what I'm telling you is that whatever double that angle is landing somewhere in the third or fourth quadrant. I don't know yet, all right? I don't know. I'll find out here in just a minute as I find the rest of the trig functions. So what's cosine 2 theta? That's our next thing. So part B, what's cosine of 2 theta? Now we have lots of formulas here, don't we? 3. That's not a lot, I guess, but we have 3 choices. Which one would you like to use? And explain your reasoning as to why you want to use that. You want to use which one? 2 cosine. So I'm going to write that. So this is one candidate. I would replace the u with theta -1. Okay. How many of you are okay with this, using that one? I guess the value in this would be that well, tell me what the value in this is. I mean, why you chose this one and not the other ones. Yeah, not only do we already know cosine theta, it was given in the it was given, right? I mean, that was given. I can't screw that up, right? Well, maybe I can write it down incorrectly, but see, the point is this. If I were to use this one, what's the other one? Cosine squared theta minus sine squared theta, right? If I use that formula, that means that I better have gotten the sine theta correct, right? I better have gotten that right, because if that's wrong, the whole thing's going to be wrong. And then the other formula is all what? In terms of sine, which again means I better have gotten sine right. So the safest formula is the one on top, because all it requires is that you read what was given to you in the problem. So that's the one I'm going to choose. All right, does that make sense? The other ones are not wrong. You'll get the same answer as long as you got the other angle correct, or the other trig function correct. So this is sine. Let's make sure we do this properly. What is cosine theta? Given to us as 3/5, and then squared. So remember what cosine squared theta meant? It meant that you figure out what cosine theta is first, and then you square it. So that's why I put the 3/5 in there and then squared. And then minus 1, which is, let's see, 2 times 9/25. Squaring a fraction, you square top and bottom. And then 2 times, forgot the minus 1. 2 times 9, 18. So I've got 18 over 25 minus 1. I have to get a common denominator here. So 18 over 25 minus 25 over 25, which gives me negative 7 over 25. That's cosine 2 theta. So I know what sine of 2 theta is, and I know what cosine of 2 theta is. Can you tell me what quadrant 2 theta is in now? Third. 2 theta is in the third quadrant. I don't know what it is, but I know it's in the third quadrant because both the sine and the cosine are both negative, which forces me into the third. Now, let's do part C, which is to figure out what tangent 2 theta is. And there's a formula for it, right? That complicated looking formula I gave you. And I told you that very, very seldom have I ever used that formula. And that's because I can just use the fact that tangent theta is sine 2 theta over cosine 2 theta. And I just figured out what both of those were, didn't I? So I already have that information. Sine 2 theta, we said, was negative 24 over 5. 25. And cosine 2 theta was negative 7 over 25. So if I multiply, do the reciprocal up here, flip it, and then negative divided by negative is positive, you get what? 24 over 7. And just leave it like that. We want the exact values, so we just leave it as that fraction. Is that okay? Flip. Any questions? This, again, will be on the test. Okay, the next set of formulas are they're not explicitly written in the, well, they're in the book, but they don't give it a good name, these formulas, but they're on your formula sheet. And I believe they're called, what, power reducing formulas? This is 863. Power reducing formulas. And these formulas do exactly what they say. They are used when you want to reduce a power. So the formulas say, first of all, sine squared u equals 1 minus cosine 2u all over 2. Is that correct? Is that what you have on your sheet? Power reducing formula? Now, so many times this is used, and you don't want it to be one big fraction like that, that I prefer to write the formula, and you can put this on your sheet if you'd like. I prefer to write it this way. Excuse me. Or you could even pull the 1/2 out like that. So this is the way it's written on your sheet. I split it into two fractions because I have two terms on the top, one on the bottom. So here it is as two fractions. Do y'all see that? And then if you factor out of 1/2, it's just this. So feel free to use that on your formula sheet. Going back to what I was showing you earlier, what was that thing I had? This, come on. Okay, look at this right here. Cosine t times cosine t is cosine squared t. If you look at your power reducing formula, how can I power reduce cosine squared t? As what? 1 plus cosine 2t over 2, right? So I said it's like a 1/2 that you could just pull out of everything. Notice from this line to this line, forget all the other crap, but notice that cosine t times cosine t, here's the 1 plus cosine 2t, and then where's the 1/2? It's out here. Okay, I actually pulled it way out of everything. So I'm just showing you this is that formula in a problem like later on in other math classes. So that's why I prefer this one over this one. All right, cosine squared u is on the formula sheet 1 plus cosine 2u over 2. And then going through the same logic, this is 1/2 plus 1/2 cosine 2u. And this is 1/2, and then in parentheses, 1 plus cosine 2u. So what the power reducing formula allows you to do is it allows you to take something that's squared, reduce the power, and have a new expression with the power gone, right? You see the squared is gone over here? But what do you give up for that? What's the sacrifice, I guess? What's the give and the take here? You can get rid of the power, but what do you have to do then? What happened to the angle? The angle doubled. Do you see that? You go from cosine squared u, right? This had cosine u in it, and your new formula has what? Cosine 2u. So it's nice you can get rid of the power, but now you double the angle, and that can cause issues later. But it still allows you to reduce the power. All right? Is there one for tangent? Yes. It's just the ratio of these two fractions right here, right? So if you were to take this and divide it by this and do the reciprocal thing, the 2's would cancel out. So you just get 1 minus cosine 2u over 1 plus cosine 2u. So this formula is, I think, do you think it's kind of easy to remember? I don't know. I mean, you have to kind of remember it, but it's the same formula for both. The only difference is subtraction and addition. So I always remember it with, sine s subtract, and cosine is just not that. I mean, I don't know how else. That's the way I remember it. If it has the s, sine subtract. If it's cosine, well, combine. Yeah, combine through addition. I don't know. However you want to do it. Everyone, you got your own way, all right? My brain doesn't like to memorize things, all right? Which is why I'm okay with formula sheets. All right, so those are your 3 power-reducing formulas. So let me show you one of the ways it's used. This will happen in Cal 2, but I mean, it's in the book. I'm not pulling this like he's giving us Cal 2 problems. This is a problem they put in the book intentionally because they know you're going to see it in calculus later. So as an example of this, 8.6.4, rewrite cosine to the 4th x in terms of trig functions with powers of 1. In other words, I want you to tell me if there's a way I can rewrite cosine to the 4th x so that it's got trig functions in there, but none of them are raised to a power more than 1. All right? So your answer cannot have cosine squareds in it or sine squareds in it. Everything has to be in terms of sine and cosine with just the power 1, which means just sine and cosine. Make sense? That's what I want. So let me start off with this expression, cosine to the 4th x. And somebody tell me how I can rewrite that. I mean, cosine to the 4th x is the same as what? Cosine squared, squared, right? Or you could write it this way. Cosine squared x times cosine squared x again. Can't you? Oh, I should add something in here, sorry. In terms of the sum or difference. That's kind of important because I could be a smartass here and I could say, oh, sure, you want me to write that so it doesn't have cosine to the 4th power? I'll just write cosine x, cosine x, cosine x, cosine x. Okay, there you go. Now there's no more power, right? Cosine x times cosine x times cosine x times cosine x. That's the same as cosine of the 4th. So that's kind of being a smartass. So if I want to be real specific, I want this to be like addition and subtraction between sines and cosines. So far, I've rewritten it. I still have a product. I still have squared and squared. Do y'all agree this is cosine of the 4th, though? Yes? All right. Now, cosine squared, though, I can power reduce, can't I? What's the formula to power reduce cosine squared x? Well, 1 plus cosine 2x over 2, right? The formula I just gave you? Or you could write it the way that I told you I like to write it, which is this way. Right, that right there is just that one, right? Agreed? And then the other one can be written the exact same way. So I can write this one over here with multiplication, 1/2, 1 plus cosine 2x again. Are we good? Have I achieved what I was trying to achieve? Have I rewritten the problem in terms of sine, cosine, sum and difference with powers 1 on the trig functions? Yeah and no. I mean, yes and no, because there's still multiplication here, isn't there? Which means if I FOILed this out or multiplied that all out, I would actually get some more squared terms in here, as you're about to see. Look, since this is all multiplication, let's put the 1/2 and the 1/2. Multiply those two together, you get 1/4, don't you? Then don't I have to do what's in this parentheses times this, what's in this parentheses? Yes? If I'm going to multiply this out? So that's like a little FOIL action here. I don't like FOIL. What's the technical word for FOIL? Expansion, expanding two things. That's the word for it. FOIL only works when you have 2 and 2, right? So what happens if you have 3 and 4? 3 terms and 4 terms. You don't say FOIL, you say expand. So we are going to expand this. 1 times 1, right? Gives me what? 1. 1 times cosine 2x is cosine 2x. And then, no, I'm ignoring the 1/2 because I already took care of those, right? Those are in the front as a 1/4. Then I do cosine 2x times 1, which gives me another cosine 2x. And now here's the part that causes the issue. What's cosine 2x times cosine 2x? It's cosine 2x squared, which means I need to write it like that. You see that? It's cosine 2x squared. Now, all of this needs to be in parentheses because I had a 1/4 out here in front, right? That 1/4 applies to everything. Do y'all follow that? Have I rewritten this in terms of trig functions with addition powers being 1? Almost. What's wrong with this? I still have a cosine squared. Well, that's okay because I know how to reduce a cosine squared, right? I can apply a power reducing formula to it. So I'm actually going to do another power reducing formula on just this guy right here. Yes? Do y'all see that? Okay. So let me do it. I'll leave the 1/4 here. I'm going to just put 1 plus, oh, what happens, I can put these two together, right? An apple plus an apple is 2 apples. So that doesn't become squared, right? Because it's being added together. This one right here, plus, now I'll do it in a different color. This piece right here, by the formula, becomes 1/2. 1 plus cosine, drum roll, 4x. Why is it 4x? Because the formula says if you want to reduce the power, right, you have to double the angle, no matter what the angle was. So if the angle was already 2x, you've got to double that. And now it becomes a 4x. Now let's distribute this 1/2 through. And then the last line, I'll distribute the 1/4 through. Let's see what we get. Leave the 1/4 out here for now. 1 plus 2 cosine 2x plus 1/2 plus 1/2 cosine 4x. Distribute 1/4 through the whole thing now. 1/4 times 1, 1/4. What's 1/4 times 2 cosine 2x? Wouldn't that be 1/2 cosine 2x? What's 1/4 times 1/2? 1/8. And then 1/4 times 1/2 is going to be 1/8, then cosine 4x. There's one more thing I could do here. Do y'all see it? Those are like terms. 1/4 plus 1/8 is 3/8. So we are done at this point. 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x. What I've done is I've rewritten cosine to the 4th as a bunch of trig functions being added together and subtracted. There's no subtraction here, but added and subtracted, sum and difference of trig functions, none of which are squared. They're all to the first power. Which, believe it or not, becomes useful later on. Because what we'll want to do in a calculus class is we'll want to do this operation again called integration, and we're going to want to do it on this, and we're going to go, whoa, that's even though it doesn't look that bad, it's pretty complicated because of the 4th power. So what we do instead is we use all these identities to get it down to here. And then what happens is instead of doing it on the cosine of the fourth, we do that operation on each one of these. And it's very simple to do it on a number. It's very simple to do it on this, and very simple to do it on this. So in other words, the doubling of the angle and stuff in there does not affect our ability to do that operation later. So we prefer this. Imagine how complicated this problem would have been had we started with cosine to the sixth. Because then you would have had cosine squared x, cosine squared x, cosine squared x, which means you would have had 3 of these, which means when you expanded them all out, this would be a disaster. And you would have to do power reducing actually several more times before you could get things to work out. In a Cal 2 class, we call that a torture problem. We give the student like cosine to the 8th, and we tell them to break it down. And so it's like the entire page written sideways because you need like the lines. There's not enough room on one line for everything. It's really a disaster. I don't think I torture my students in class with that. I think that I just give them probably a cosine to the 6th problem. Oh yeah, look, wow, I went right to it. Check this out. That was unintentional. There's that integral, cosine to the 6th. Okay, so I did give them cosine to the 6th. Let's see what they did. We wrote it as cosine squared x cubed, but what's cosine squared x? 1/2, 1 plus cosine 2x, all of that cubed. Do y'all follow me? I cube the 1/2, it becomes a 1/8, and that's why it's out here. Then I've got to cube this. When I cube that, which I don't show the work, notice in Cal 3 class, in Cal 2 class, we do not show the work of cubing this. It's assumed that you could get that, all right? So we do that. Here it is. And then what we do is we go, okay, crap. This one is squared still, right? So I power reduce that one. And you can, well, you know what? I don't even show the power reducing breaking down of that. I just stated it in class. Oh, and just by power reducing formula, we can get to this. Do you see what I'm saying? Like, it's like I don't show you how to add 7 and 3 together anymore, right? I don't show you how to multiply numbers together. I don't show you how to solve linear equations. I don't show you how to factor difference of squares. In a Cal 2 class, we don't show you how to do all the stuff that you were supposed to have saw in pre-Cal. Understand? It just builds on itself. So yes, this step from here to here should take about a page of work, but it shouldn't be something that the instructor has to show you how to do. You with me? Yeah. I mean, look, it was like that for me too as a student. You know, I hated the fact that, you know, I wanted someone who would go up there and show me every single step. There's just not enough time. I mean, imagine if I had to show this, and then this one's just as complicated. If I had to show this one and this one, then that's the whole class. I mean, that's pretty much, I mean, you have hour, 40 minutes. That's 20 minutes right there. Where's the calculus going to happen, right? All right, so that's why we're doing it in here. All right, so what else do we want to be able to do? Oh, okay, yeah. How about this? This is a good problem. I'm so curious to see what you'll do with this. 865. Solve, solve sine theta cosine theta equals -1/2. And this is a good problem. I mean, it's not great, it's just good. I want a general solution. General solution. I'm thinking on your test on Wednesday that for all equations that I give you to solve for, I'm just going to ask you for general solutions. Like, I'm not going to ask you at all for like the solutions between 0 and 2 pi. So you don't have to plug in values of k. You just give me the general solution, you move on. Does that sound like a plan? Okay. All right. So what is the most common mistake I see on a problem like this? Let me tell you. Or does anyone want to share what the most common mistake is? If they see it, what people do, what you're not allowed to do? Divide by cosine. If I divide by cosine, I'm going to get like a secant over there. That would probably lead you in the wrong direction. But I'm trying to solve an equation, right? Yes? So the thing that I see is people will say, oh, there's multiplication here, right, between sine and cosine. So I'll just set each one equal to what? If these two have to multiply to be negative 1/2, people will say just set each one equal to negative 1/2, which is completely wrong, right? If you have things that multiply together to be 0, right? If I had sine theta cosine theta equals 0, then I could set each one equal to 0. That's called the zero factor property. The only way two things can multiply to be 0 is if one of them is 0. But if I tell you that two things multiply together to be negative 1/2, does that mean that one of them has to be negative 1/2? No. You could have what? 4 times, what? Negative 1/8? What's 4 times negative 1/8? Negative 1/2, right? Are either one of these negative 1/2? No. Do you understand what I'm saying or not? I was watching this video the other day. Okay, I shared this with one of your classmates. I was watching a YouTube video because I'll get on and I'll search for like math, people who do YouTube videos, trying to just find like different approaches to things. And I found this guy. It's the first time I'd ever seen this guy. He was just outstanding. I mean, it really gave me something to aspire to. I was like, wow, this guy is great. Just outstanding. And I was watching a couple of his lectures. He was doing like Cal 3 problems, Cal 2 problems. And I was just like, man. And then after watching about 3 or 4 of his videos, I finally figured out what it was that made him so good, because he was explaining everything kind of in the terms that I do. I mean, I'm not trying to compare myself to him, but the thing that was different is that every time he engaged his class, I mean, you could hear on the video like people were like just like yelling back to him. I mean, it was all the back and forth was there on all his videos. That repertoire he had with his class was just outstanding in all of his classes. I can't force that. I don't know if we need to go to like whips or what, but like, I've been trying in this class to get people to want to talk and just tell me how they're feeling, and I just can't do it. So I don't know what I need to do. Buy donuts the first day and just like let everyone, I'm not sure. I'm trying to get you to engage me. It's just, it seems like I'm having a real hard time. We don't have much time left in the semester, so I'm not quite sure we can recover from that. And I know we had a rough start, but I encourage you in your future classes to not be the student there afraid to sound stupid or whatever. Just say how you're feeling. This is your education, right? You want to pass for whatever goal you have. You need to get through this class, right? You are the one who controls your destiny. So do you understand that two numbers, when you multiply them together, if they turn out to be 0, one of them has to be 0? Yeah? All right. This is not the case. So what I'm going to do here, and I think it's best if I just show it to you the first time, is I'm going to realize that looks a whole lot like the double angle formula for sine, right? Isn't sine 2 theta equal to 2 sine theta cosine theta? The only thing that's missing here is what? Like, what would I need to have to make this match that formula exactly? A 2 in the front, right? Well, it's an equation. Can't I do anything I want to an equation? Like, not anything, but I can multiply both sides by 2. All right. That's not wrong. I mean, it's not going to change the answer. As long as I don't multiply by what? And what's the only thing you can't multiply both sides of an equation by? What's the only thing that causes a problem? 0. Because if you multiply both sides by 0, you get 0 equals 0. Big deal. I mean, you've done nothing other than zeroed out the equation. So that's why we're not allowed to do it. Okay, so now this is more like it, right? Because what? Now don't go through here and divide by 2 now. Because you just multiplied by 2, right? So don't go undoing what you just did. Now rewrite the left-hand side as what? Sine 2 theta is -1. Now you have one trig function instead of two trig functions. And so now you're just asking yourself, when is sine, my argument's 2 theta, I'll deal with that in a second, but when is sine by itself -1? So I go to my unit circle, sine is the y coordinate, it's going to happen down here, right? So what angle is that? 3 pi over 2, and I want all angles, so plus 2 pi k. And I need my argument to be that. And my argument is 2 theta, right? Not just theta. So I want my argument inside to be 3 pi over 2 or any 2 pi multiple of 3 pi over 2. Well, no. Any 2 pi multiple added to 3 pi over 2 would take me to that same angle. And finally, just divide by 2. 3 pi over 4 plus pi k. Okay, so that's just showing you how you can have this trig equation that, and without the double angle identity that we just got today, you really wouldn't have had a whole lot of options as far as how to get that. All right, there are some other formulas in this section. 8, 6, 7. The half angle formulas. Yeah. What was it? 6, 8.6? Thank you. Half angle formulas. These are the ones that are not on your formula sheet. All right. And here's what they are. If I have sine of u over 2, this is equal to plus or minus the square root of 1 minus cosine u over 2. Cosine of u over 2 is plus or minus square root of 1 plus cosine u over 2. And tangent of u over 2, so put these on maybe the back of your formula sheet, plus or minus square root 1 minus cosine u over 1 plus cosine u. Anybody have an idea of where these formulas come from? They look very complicated, don't they? They look like, wow, this is just, ugh. Jot them down and I'll explain where they came from. While you're jotting those down, I'll just put below it where they came from. You don't need to know where it came from. I just want you to see it. Okay, so look at, this was the formula I gave you for power reducing, right? What we said with the power reducing is that whatever angle was here, this angle got doubled, right? If you read it backwards, then you could say whatever angle's here, right? This is half of it. So whatever angle's here on the left is doubled on the right side, or whatever angle's on the right side, you half it to come back. So what if I replaced this right here with u? Then this side would have to be replaced with what? Half of that, u over 2. So do you agree that this still works? If I double u over 2, it gives me u, yes? And now just take the square root on both sides to get rid of the squared. If I take the square root on both sides, you always have to do plus or minus, don't you? And so the square root kills off the sine squared, which just leaves you with sine U over 2, which is that, and then plus or minus, and then that. So it's the same formula, which is why the formula sheets don't usually put them, because you can always extrapolate these formulas from those. But they are called half-angle identities or half-angle formulas. Now, the bad thing about these is that it involves a plus or minus, which means that you often have a hard time determining which one it, well, you have to determine which one it's going to be, the plus or the minus, all right? So let's do an example using this. 8, 6, 7. What if cosine U is negative 3/5? And I tell you that U is between zero and pi. All right? I want us to find A, sine of U over 2, B, cosine of U over 2, C, tangent of U over 2. So what's sine of half the angle, what's cosine of half that angle, and what's tangent of half that angle? We will start by just figuring out where in the world this thing is. What quadrant do I have to be in here? Well, I can't be in 3 or 4 because of my restriction here. I had to be between 0 and pi. That was given to me in the problem. And then the fact that cosine is negative, right, makes me have to be where? In quadrant 2. So I can get rid of this one. So I'm somewhere in there. And I can draw a triangle off of this, can't I? My reference triangle will look like this. I know that the hypotenuse is 5, and I know that the adjacent side is what? Negative 3, right? Negative 3 because I am in the second quadrant. My x-coordinate, which is my adjacent side, has to be negative. And then by Pythagorean, I know that my, what? This will be 4, right? And now the angle I'm dealing with here is U, right? This triangle is developed off of the idea of the angle U. I'll put U in here even though technically U is this angle right there. So let's try part A. What is sine of U over 2? According to the formula, it's plus or minus the square root of 1, what? Minus cosine of U. Well, what's cosine of U? We actually had that in the problem, right? Negative 3/5. Yes? So minus a negative, right? Be very careful with that. It's minus a negative all over 2, which is plus or minus square root 1 plus 3/5 over 2, which is plus or minus, I'm going to simplify this. This is 8/5 over 2. What did I do there? Common denominator on the top, right? 1 plus 3/5 is 8/5. And then divide that by 2. So 8/10, which reduces to be 4/5. Do you all agree with that? Is it plus or minus? See, we're not saying it's one or the other here. We're saying it's one of those two. Now we have to figure out which one it is. So the only way I'm going to be able to determine the value of sine of my angle over 2, right, of half that angle, the only way I'm going to determine that is if I know what quadrant that angle is in, right? I need to know what quadrant U over 2 is in. So come back up to this information that we had about U. Here's my information about U, right? I'm just going to jot that down here. 0 was less than or equal to U was less than or equal to pi. So if I come through here and I divide everything by 2, that tells me what U over 2 is going to be, right? U over 2, so the left side here, 0 divided by 2 is 0. U over 2 stays here, and then over here is pi over 2. So that tells me the angle U over 2 has to be between 0 and pi over 2, which means I am in quadrant 1, right? We are here, quadrant 1. What is the value of sine in quadrant 1? Positive. So now I can say, all right, I know this for sure. It's positive root of 4/5. Yes, you could change that into 2 over root 5, and yes, you could change that into 2 root 5 over 5. All of those answers are the same. Now, did I really have to draw all the triangle to make this thing work out? Did I really need this? I didn't, because the formula for this requires that I know what? Cosine of U, right? Which is what I gave you in the problem. But that's the only reason you wouldn't have had to do all that work. If I would have given you sine of U, then you would have had to have gone through all this work, which is why I'm showing it to you. Does that make sense? All right, so what would be the difference between sine of U over 2 and cosine of U over 2? Let's see what would change here. That would become a what? Positive, which means this would be a negative, right? Which means this would not be 8/5, it would be what? 2/5, and this would not be 4/10, it would be 1/5, right? This would be 2/5. 2/5 divided by 2, that should turn out to be 1/5. So the difference here is that you would have root of 1/5, and then positive or negative. Well, you're still in quadrant 1, so it should be positive. So you should get root 1/5. Yes? Y'all with me or not? I don't want to go through all that work because we just don't have enough time. You feel like you could do that? Just replace that sign in there and rework it? And then what would tangent be? Tangent of theta U over 2. You could take this answer, the answer for sine, and divide it by the answer for cosine and get that. That's the way I would do it. Don't use the formula. Just do the answer you got for sine, divide it by the answer you get for cosine, and then just take that ratio, and that's your tangent answer. All right, that is it for 8-6. Homework, page 659. I think that 7 through 17 odds, great problems right there. Definitely in the category of what you'll see on the test. Maybe number 69 through 73 odds. Those are solving equations. So you'll have to use these formulas to solve those equations. All right, the last two sets of formulas. So the last section of this chapter. This is 8.7. The product to sum and then the sum to product formulas. You'll see these on your sheet. The sum, let me see, they're on the bottom right-hand side. There's 2 columns of them. These formulas do exactly what they say. They give you a way of taking the product of 2 trig functions and turning it into a sum, or if you have the sum of 2 trig functions, how you can turn them into a product. So I do not want to have to write them all down, because there's what, how many? 1, 2, 3, 4, 1, 2, 3, 4. There's 8 of them, and they're on page 662 and 663. All right? But I will show you how they are applied. Write as a sum. So let's say I gave you something like this. Sine 3 theta sine 5 theta. I want to write this as a sum. Right now it's written as a what? Product, right? I'm multiplying 2 sine functions together. Can you rewrite that so that it's not multiplication, instead it's addition or subtraction? Well, according to the formula, I do have a formula that says if I have sine U sine V, this should turn into 1/2, then in brackets, cosine U minus V minus cosine U plus V. Do you all see that on your formula sheet? So I have to match the right formula because there's 4 of them. The one I'm looking at is the one where I have sine times sine. If this were sine and cosine, I would use a different formula. So what's U for me in this problem? U is 3 theta. V for me is 5 theta. Now I could switch it because multiplication, the order doesn't matter, does it? I could, but let's just stick with, U is the one on the left, V is the one on the right. So this is just apply the formula. Plug and chug is what we like to say here. So this becomes equal to 1/2 in brackets cosine of U, 3 theta, minus V, 5 theta, minus cosine of U, 3 theta, plus V, 5 theta. This is 1/2. 3 theta minus 5 theta is negative 2 theta minus cosine of what? 8 theta. I'm going to do one more thing here. See if you can follow this. What did I do there? I distributed the 1/2 through to the both terms, but something else changed. The negative 2 theta in here turned into a 2 theta, and nothing else changed. So am I allowed to do that? Why? Because of the even odd property of cosine, right? Cosine of negative U is the same as cosine of positive U. That's on your formula sheet, right? Does it work the same for sine? What's sine of negative U? Negative sine of U. So that if that had been a sine, I still could have made this a positive 2 theta, but then it would have changed it to a negative out here. So just be aware of that. Now let's try something else. Let's turn a sum into a product. Where was that homework problem? Watch this. You'll like this. I think you'll like it. Having a hard time figuring out what you'll like. 872. I'm going to give you an equation to solve. I'm actually taking this problem out of the previous section's homework. I want a general solution to this equation. Now, like I just said, this problem came out of the previous section's homework. So we didn't have the formulas that I just gave you yet. But when you do your homework, I think you can use anything you want on your homework, okay? There's no restriction. It's kind of like, you know, if any of you have ever used a circular saw, you know, to cut a piece of wood, you know, if I hand you a handsaw and a circular saw, you're probably going to use a circular saw, right? So it's kind of like when you look at all these problems for your homework, use the entire formula sheet. Don't be like, oh, wait, in this section, they only want me to use this formula. No, use it all, because in the real world, you will never be limited to just like, you know, just these formulas you can use, right? You want to use the whole thing. So if I were doing this problem, if I looked at this, I'd say, okay, I could use the double angle formula to turn sine 2 theta into what? 2 sine theta cosine theta. That's double angle formula, right? But instead, let me try this. Let me move everything to one side of the equation. I'm going to put that theta in parentheses, even though I don't need to. Do you have a formula that turns subtraction of two trig functions into a product? Do you have anything that says sine u minus cosine v? Do you? What do you have? No? No go? So, but I'm looking there because what if this had been able to become a product? Wouldn't I already have it factored then? I mean, wouldn't this all be factored out? I'd have something times something times something equals 0. Do you see what I'm saying? So because of that, not having a formula to go here, what are our formulas for sum to difference? It only allows sum to product. You can only go what? Sine plus sine can go into a product. You can do what? Sine minus sine. You can do cosine plus cosine, cosine minus cosine. That's it. So if it's a combination of sine and cosine like this, you're going to be stuck. With me? But I'm going to continue this. I would be forced here to do this, just to show you how this would work out. So what could I do on the left side here, now that I've written that as a double angle formula? What can I do here? Set what to 0? Set that to 0. That's, well, there's not multiplication though. It's subtraction, so I can't do that. Can you factor this side? What do these both have in common? They have a cosine, right? So could I do this? Cosine theta, 2 sine theta, minus 1. I could do that, right? Factor a cosine out of each of the terms. And now can I set things equal to 0? Because I have multiplication between them, right? I can set this one to 0. And I can set the other one to 0. And work those out. I'm not going to work those out, but do you see what I'm saying? Use the double angle formula, get a GCF out, set each factor to 0. Each of those should be relatively simple to solve. When is cosine 0? You go to your unit circle. Where's the x-coordinate 0? Give me the general solutions. Here, you move the 1 over, divide by 2. When is sine theta 1/2? Same thing. Go to your unit circle. Okay, that problem didn't work out the way I wanted it to. So let me change it just slightly to show you. I'm going to make up my own then. I'll force it to happen. What if it would have been cosine 2 theta equals cosine 3 theta? So now move everything over to one side. This will be good because hopefully you'll see the difference between this problem and the one before. Can I see, right now I cannot set each of these to 0 because there's not multiplication between them. But if I can turn this sum, even though it's subtraction, it's still considered a sum. If I can turn this sum into a product, I can then do a factoring, right? I mean, I can set each factor to 0. So do we have a formula that does that? Yes. So the formula will be, let's see, cosine, I'll write it down on the side here. It's cosine U minus cosine V equals -2 sine U plus V over 2. I'm out of room. Sine U minus V over 2. Is that what y'all have on your formula sheet? Yes. Cosine of U minus cosine of V equals -2 sine of U plus V over 2 times sine of U minus V over 2. So this whole thing becomes -2 sine of, what's U plus V? U plus V. 5 theta over 2 times sine of U minus V. -theta over 2 equals 0. Questions? I don't like the negative in here. Why? I don't know. I just don't. So can I get the negative out of here? Can I change sine of -theta over 2 into sine of positive theta over 2? Yes or no? Yes, but what will I have to do? If I'd have to make this a negative, right? Outside, which would change this out here to a positive because it's basically like a -1 that would have to come out of here. So I'm going to rewrite this as 2 sine 5 theta over 2 sine positive theta over 2 equals 0. And now that this thing is factored out nicely, I have multiplication. Oh, whoa. That's not multiplication, right? Sine 5 theta over 2 is not sin times this, right? This is a function, sine of that. So I have multiplication, set each factor equal to 0. Can I throw out the 2? Yeah, 2 is not going to have any effect. So I want to know when sine of 5 theta over 2 is 0, and I want to know when sine of just theta over 2 is 0. Where on the unit circle is sine 0? 0 and pi? And that would work out for this one also, right? Both of these? So for both of these, I want the arguments to be equal to what? How do you say 0 and pi, all the different solutions, 0 and pi? Pi k? Pi k over there? So I want my arguments, both of them, 5 theta over 2, to be equal to pi k, and I want theta over 2 to be equal to pi k. Why am I not using 2 pi k? Yeah, it's just on the other side. So instead of going all the way around, having two different general solutions, I just go jump back and forth. All right, and now how do I get theta by itself? How about multiply by the reciprocal of 5 over 2? So multiply both sides by 2 over 5. 2 over 5 pi k. This one, theta equals 2 pi k. There we go. That should be when that equation is true. All right, I think we've reached a point where we can say that's enough information for the test. 646, or so, 664. The only things from here, I'm just going to have you practicing writing these back and forth. So number 7, number 9, 17, 19, That's good. Also, page 666. Page 666, just so you know, it has a summary. It has a summary of all the different formulas from the section all on one page, or from this chapter on one page. So it's just so you know it's there. I'm going to work on your review in the next few days, and I'll let you know what happened. So here's what happened. The other day, I gave that handout to say who's going to be here and who's not. And I had a little bit of an issue because I had the stack up here. I was trying to get to my next class. I left the stack up here. I haven't seen it since then. So my guess is that someone found it and they've turned it in, and it's going to get to me eventually. All right? So all I need right now is for you, I'm going to call attendance, all right? And you're going to reply to me by letting me know you're here. But what I want you to tell me is this, and let's not try and make this too complicated, all right? When I call your name, you say yes, meaning you're going to be here next Wednesday. If you respond to me calling your name saying no, that means you're not going to be here, all right? You don't need to say here or yeah, just say yes, meaning you're going to be here Wednesday. No, meaning it's going to be some other time, all right? Hopefully those other sheets will turn up. All right, here we go. See if we can pull this off. Alicia? No, you're not here, or yes? No, I'm just kidding. Never mind. And once I call you, you can go. Gabe? David? I'm sorry, I'm going to mess your name up. De La Vega. Aria? Donata? Donata. Let me turn off my recording real quick.